Question 27. A 0.487 gram sample of quinine, 324 grams per mole, is combusted and found to produce 1.321 grams of carbon dioxide, 0.325 grams of water, and 0.041421 grams of nitrogen. Determine the empirical formula as well as the molecular formula. Yeah. Let's write out your equation just so that we can see where everything comes from, okay? You've got quinine on the left, and then same thing as before. Don't slack off in your chat. If the last thing didn't make sense, then I need to be hearing more answers from you, yeah? Clearly, just listening to it isn't cutting it, okay? What is combustion? What am I reacting quinine with if the question says I'm combusting? It's in air. What's the component of air? Oxygen. Okay, so what's the formula that oxygen exists as? Because I know oxygen is O, but in real life it floats around as O2. Good, thank you. And then on the right, you've got carbon dioxide. Tell me what's the formula for carbon dioxide? CO2. They've also got water. What's the formula for water? H2O. And then nitrogen. There's also nitrogen in here. What does nitrogen exist as in real life? What does it float around as? Good. Nitrogen's also diatomic, so it's N2. So there's CO2 plus H2O and there's N2. Yeah, I'm going to label what I've got on here. I've got 0.487 grams of quinine. I've got 0.324 grams of water. And I've got 0.0421 grams of nitrogen, and then the CO2 was 1.321. They also told me quinine was 324 grams per mole. Okay. They want empirical formula as well as molecular formula. Go back to when we did this for the first time in module 2. What do you figure out first? Empirical first or molecular first? You figure out the empirical first. Okay, now give me the definition. Finish off my sentence for me. Empirical formula is the simplest whole number ratio of what? Starting with an E. The little components of the formula, your periodic table of the each element in the compound. It's the simplest whole number ratio of each element in the compound. Now, okay, cool. Now, it's the simplest whole number ratio in terms of what? They've given me mass. Is it whole number ratio of mass? It's whole number ratio of, what do you always read ratios in terms of? Like when you're doing stoichiometric ratio, it's always simplest whole number ratio in terms of moles. Guys, every time you're doing ratio, it's always the moles. Yeah. And then, yes, the coefficients, if it's a balanced equation, that's also in terms of moles. It's the simplest whole number ratio of the elements, and it's the ratio in terms of the mole. So you're not doing ratio by mass. Yeah. Now you're used to just being given the mass of the element itself and doing mass and molar mass for just the element. Here, that doesn't exist. You don't get given anything for a single element. You get given it for carbon, you get given it for hydrogen, you get given it for nitrogen. Yeah. But it's fine, guys, because you can do ratio within the formula as well. Okay. So let's say, for example, I want carbon. I'm going to start off with carbon. I know I need all of it, carbon, hydrogen, da da da. I'm just going to start off with carbon. Tell me, in which formula in the screen right now do you see a carbon atom in? Which of these formulas? Quinine, O2, CO2, H2O, N2. Which one has carbon in it? Okay, cool. So what that means is I'm going to get the amount of carbon atoms from the carbon dioxide molecule, yeah? However, I can't just say it's 1-to-1. I have to check if it's actually 1-to-1. There is no subscript on the carbon. What is the subscript? Okay, cool. So in this case, it is an invisible one. My amount of carbon is going to be the same as my amount of CO2 because it's a 1-to-1 ratio, okay? So mass on molar mass, 1.321 grams divided by molar mass for carbon dioxide is 44.01. What do you get for the moles of this one, please? 0.030015. Thank you. So that's my carbon done. Okay, that's my carbon done. Yeah. Now, guys, from the previous question, the carbon on the right is equal to the carbon on the left. It doesn't mean it's always from quinine. Okay, it might be from a combination of different things. Yeah. Now, here's the thing though. Let me do my formula for quinine. Let's go CXH, or I can't do X because I've got 4 elements here. WCWHX NYOZ. All right, so that's quinine. I don't know what quinine is, but it has a bunch of carbon, hydrogen, nitrogen, and oxygen in it. Okay. Now, all of the carbon on the right has to equal to the carbon on the left. It has to equal all of the carbon on the left, all of wherever it came from. Yeah. However, guys, on the left, how many places do you see it showing up? There's 2 formulas on the left. How many formulas do you see carbon in? 1. Okay. Which means if you get 0.03 moles of carbon on the right, do you have to divide that up between quinine and oxygen, or is that all of the carbon in just quinine? No, I don't have to divide it up because it doesn't show up anywhere else. All of the carbon on the right has to go into quinine because the other formula is just oxygen. Yeah? So this is the carbon, let's label it. It's all of the carbon in quinine. Okay, cool. So we've established that. That's actually what I want. I want the amount of each element in my unknown quinine. Yeah? Now I do the same thing with the hydrogen. Same question, guys. On the right-hand side, what formula do you see hydrogen in? Only H2O, which is good. I don't have to add it from a bunch of different spots, yeah? How many hydrogens in each H2O? 2. From last lesson, molecule to atom, you multiply by the subscript. So guys, if I've got the moles of H2O, what do I multiply it by to get the moles of just the H? What's the subscript? How did you get that number before? It's a subscript 2. Okay, and then I do the same thing. 2 times mass on molar mass. 2 times it's 0.324 grams divided by 18.016 grams per mole. Don't forget to multiply the 2 when you pop it in your calculator. What do you get for the moles of H? Don't forget the 2 when you're multiplying. Did I copy down 0.324? Sorry, guys. The mass from the question is 0.325. It changes your answer because you're doing so much here, it changes your answer, yeah? Can you pop it back in the calculator? 0.325, not 0.324. I would normally let it go, but it changes your answer quite a bit. There's quite a bit of working out that we're doing here. Thank you. 0.325, not 0.324. Yeah, thanks. Okay. And then next one is nitrogen. Let's do the ones that only show up in one spot first. That's easier. Yeah, nitrogen only shows up in N2. Have a look at the subscript. If I want the amount of nitrogen N atoms, what do I multiply the nitrogen molecule by? Molecule to atom times by the coefficient. What is the coefficient on the nitrogen? N2. Good. So your original answer was correct, times by 2. Good. Okay. Same thing. 2 times mass on molar mass. 2 times 0.0421 grams. Each nitrogen is 14.01. If it's N2, that's 28.02 grams per mole. Okay, what do you get for the moles of nitrogen? Don't forget to multiply by the 2. Thank you, 0.003004. All right, now, this is where we're going to slow down because the only element we have left is oxygen. Yeah? Before we even go to do the working out, the last thing I'm looking for is oxygen. Yeah, this is what I'm looking for now. So let's make a note of it here. So before we even do the working out, I need to make sure you guys know what's going on. Where does oxygen show up on the right? Give me all of the formulas. CO2 as well as H2O. Good. Where does oxygen show up on the left? You can just say quinine. You don't have to type out the letters if it's easier. Where does oxygen show up on the left? Quinine as well as the O2 molecule. Good. So guys, when I get the total amount of oxygen on the right, yeah, did all of that come from quinine? Yes or no? No, because some of it came from O2. Yeah. So what does that mean? When I get the total moles of oxygen on the right, I cannot equate that to quinine. I have to subtract some of the oxygen that came from where? If I only want the quinine amount, I have to subtract the oxygen that came from where? What else is on the left that accounts for some of the oxygen? I have to subtract some of the oxygen that came from this. Good. Okay. The total amount from quinine is what's on the right minus some of the parts that came from O2. Yeah. Okay. So N of oxygen, our total N of oxygen on the right-hand side, you guys told me it came from CO2 as well as H2O, yeah? Is the moles of oxygen from CO2 plus the moles of oxygen from H2O. Okay, so the same thing, let's deal with it one at a time. What's the subscript on oxygen for CO2? Molecule to atom times by the subscript 2. Cool. So the moles of CO2 times 2 gives you the amount of oxygen plus the amount of oxygen from H2O. What's the subscript on oxygen in H2O? It's not there, which means it's 1. 1 times the moles of H2O. Okay? Then you pop it in the same way, 2 times mass on molar mass plus mass on molar mass for that one. So you're going to go 2 times for carbon dioxide, that was 1.321. 1.321 grams, 44.01 grams per mole, plus for water, that was 0.325. And then the molar mass of water is 18.016. What is the total amount of oxygen on the right? Thank you. 0.0780. Well, okay. And then normally it would just be the amount from quinine, except you guys identified that some of the oxygen on the left came from O2. Yeah. So this number that you've got here is the oxygen in quinine plus the oxygen in O2, okay? Because on the left, it shows up in 2 spots, all right? So let's make a note here just so that your notes are clear. If you just want the oxygen in quinine, you need to subtract the oxygen in O2, all right? So let's make a note of that so that when you go back to look at it, it makes sense. If I want to subtract it, I need to know how much I'm subtracting. So moles of oxygen in O2. What's the subscript on oxygen in O2? 2. So then I multiply it by 2. Yeah. 2 times. And then you're normally doing mass on molar mass again. But then, guys, this part should have been relatively easy from the previous question. What law did you have to apply to get the mass of the oxygen? That's the only one you don't have left. Law of law of conservation of mass. I don't even have the mass of oxygen yet. I need to go get it in the first place. So on the left, you have your, let's move that over here, 0.487 plus the mass of oxygen is equal to your stuff on the right, your 1.321 plus your 0.325 plus your 0.0421. Yeah, and then you just want the oxygen, so move it around and let me know what you get from your calculator. Minus 0.487. 1.2011. Thank you, guys. 1.2011. And then that's what I'll just keep doing my calculation with, yeah? So let me bring that back down now. 1.2011. 2 times 1.2011 grams Molar mass for O2, 32 grams per mole. What do you get for the moles of O2? Moles of O in O2, sorry. Don't forget to multiply by the 2. 0.0750. Thank you. Okay. All right. We haven't gotten the oxygen in quinine yet. Yeah. You've got the oxygen on the right and you've got the oxygen in the O2. This is what we want to do. If you want just quinine, you need to subtract O from O2. The O that came from the O2. Yeah. So now we're getting to the point of the oxygen in the quinine. So moles of oxygen in quinine is equal to moles of O on right hand side minus the moles of oxygen that came from O2. Okay, so that's your 0.0780 minus your 0.0750. I'm gonna take over here because some of you guys stored your numbers and some of you guys didn't. For this one, it's about 0.003. Okay, so now you've got all four of it. Yeah, this is you've got all four of the elements now. At this point, it becomes your regular question. This is your oxygen. This up here was your nitrogen. This was your hydrogen. And then this was your carbon. Okay? You've got the moles of each element now, which is what empirical formula is, ratio of each element. It's just that we want the simplest whole number ratio. So I'm going to simplify this ratio. For carbon to hydrogen to nitrogen to oxygen, you guys gave me 0.003, 0.036, 0.03 was for carbon. For hydrogen, you guys gave me 0.036. For nitrogen earlier, we got 0.003. And then for oxygen, you got also 0.003. Which one's the smallest number? Don't let the zeros confuse you. The more zeros, the smaller. What's the smallest number that I'm dividing by? 0.03. I divide all of it by 0.003. Guys, for the first one is 0.03 divided by 0.003. Yeah, that's off by 1 digit. The decimal place is 1 digit off. That's going to be about 10. If you pop the second one in your calculator, you get 24. If you pop the third and the fourth one in the calculator, 0.003 divided by itself is going to be 1. Okay, these whole numbers become your subscripts for the empirical formula. So for carbon, that's 10. For hydrogen, that's 24. For nitrogen, that's just 1, so I won't put anything. For oxygen, that's also just 1, so I won't put anything. This is your empirical formula. Yeah? And then we said for molecular, it has to go in a certain number of times. So we need to know the mass of this first. You got 12. Confirm for me, guys, 12 for hydrogen. 12, 12. Thank you. 0.036, 12. 12. Okay. Thank you for correcting me. And then you do the mass with the H12 now. So 10 times 12.01 for carbon, plus 12 times 1.08 for your hydrogen, plus a single 14.01 for your nitrogen, plus a single 16 for your oxygen. What do you get for the empirical formula mass? It should be 12, you're correct. I didn't update one of the pieces of working out. Thank you, 162.206. Okay, and then the molecular mass, they have to give you that in the question. They told you it was 324, yeah? So 324 divided by 162. Guys, you can sort of eyeball it. What is this? Yeah. Yeah, this has to be two. Cool. Okay, so Nova, my empirical formula is C10H12NO. My molecular formula is twice that. So what is my molecular formula? C.
C20H24 N2O2.
Good. Thank you. This is your molecular formula. All right. We alive. Barely. You guys sleep well after class? All right, good. This is a question that combined your law of conservation of mass, your molar mass calculations, your empirical formula, and your molecular formula. Yeah? All right, good. Your final answer, C20H24 N2O2. All right. Take a second to finish wrapping that up. Let me know if you have any questions. Where did the 324 come from? The 324, that it has to be given to you in the question here. They gave it to you here. That's where I got it. Yeah? Oh, if that's the only thing you're wondering, that's good. That's a good sign. Okay. Easy question to answer. Okay, cool. That's done. I'm gonna move that over here because I've run out of space. Um, I wanted to show you. That's most of your mole calculations done. Yeah, we need to move on to your ideal gases. Okay. Where did it go? All right. Question 31. At 338 Kelvin, pure PCl5 gas present in a flask has a pressure of 25.5 kilopascals. At 480 kelvins, the gas is completely dissociated into PCl3 gas and CO2 gas. What is the pressure in the flask at 480? Okay. Now, guys, this isn't completely an ideal gas law question because there are certain things that get kept constant. Yeah. Your ideal gas law is this: PV is equal to nRT. Now, I need you to make a note here for your exam take. Yeah. You use this equation if you have a value for everything. Okay, because obviously, like if something's missing, you literally just can't use it. Like you don't know what the value is, yeah? You only use this equation if you have a value for everything. And then the next thing is this. If some values are not given, but some are, so I'm saying like you've got some of it, but you don't have all of it. If some of the values aren't given, but some are, then you might be adjusting the equation yourself. Okay. So this is what you're looking out for in the exam to figure out what kind of version of this equation you're going to use. Yeah. Use this equation if you have a value for everything. If some values are given, but some aren't, you're probably using some kind of version of it. Okay. Now, I need you to have to go back and look here. Temperature's given twice. Temperature's given twice. Pressure is given once, but they ask you for pressure at another point. Okay. So it's like pressure and temperature at point one, and then pressure and temperature at point two. Yeah. Which hopefully sounds very similar because you remember like your Boyle's law, P1 V1 is equal to P2 V2. It's the same thing, but at two different spots. Yeah. So this is sort of the same vibe. Now, you can have those gas laws that we did in module two memorized, There's four equations to memorize though. And then sometimes it's not only two things that are changing. Yeah. So for example, your Boyle's law P1 V1 is equal to P2 V2. That's only pressure changing and volume changing. That's two things. Here you've got pressure, you've got temperature. Now, very hidden, moles is also changing of gas. Yeah. You start off with PCl5 gas only, and then it breaks down into PCl3 and CO2. The total amount of gas in the system is also changing. Yeah. When you have something like this, you want a version of this kind of equation. So that's Boyle's law, that's relating pressure and volume. You need a version that relates pressure, temperature, and moles. If you have every equation memorized, that's way too much, yeah? So what we're going to do is we're going to figure it out on our own, okay? This is PV is equal to nRT. What I've told you before is we did this in mod 2, but take the notes down again if you need to. If you're adjusting the equation on your own, move everything that's changing to one side and move everything that stays the same to the other side. Can Gay-Lussac's close? Gay-Lussac's law is pressure and temperature. Yes. Yeah, I think so. But that's the thing though. Remember how we said in this question there's like moles as well? Gay-Lussac's was only pressure and temperature. There's moles in here. So move everything, yeah, right? Move everything. That's why I said you can't have it. If you have it all memorized, there's always some new case. So it's better you learn to adjust it on your own. Move everything that's changing to one side and move everything that stays the same to the other side. So remember, we said pressure, temperature changing, and then moles is changing as well, which wasn't obvious, all right? But then the only thing not mentioned is volume. And then guys, can R ever change? No, R is your ideal gas constant. Who has it memorized? Who doesn't need to check the data sheet for it? Come on, units as well. Oh, now you're checking the data sheet, huh? Yeah, okay, good. 8.314, yes. So I'm gonna move pressure, temperature to one side, and then moles as well. So P, I'm gonna divide the moles and the temperature. And then I'm gonna move R is on the right, and then volume's on the right. All right, cool. That's my equation. Yeah. Now, guys, this thing is constant. Yeah, because we said we're going to keep everything that stays the same on one side. Okay, this, it's always equal to the constant, even at different points. Let's say 1 and 2, yeah, which are the numbers we tend to use. Okay, so if it's always equal to the constant, even at points 1 and 2, what that means is this, guys. If you guys get it, this will feel like I'm going through it in a bit too much detail, yeah? But for the sake of making sure everyone gets it, because I don't want anyone confused, P1 on N1 is T1 is equal to the constant. And then at another point, N2 T2 is equal to the constant. Yeah? So then all that means is I combine these two together, you get P1 on N1 T1 is equal to P2 on N2 T2. And notice how this looks like the version of some of the gas laws you got. Yeah? So you've got in like Gay-Lussac's, you've got in Boyle's, you've got in Charles, and you've got in Avogadro's. Okay, this is a version of that. Yeah? So this is the equation we're going to use. Adjust this according to whatever's changing in your question. And then here they've asked you, just rearrange it for what they want. They've asked you for the pressure at 480, which is the new temperature. Yeah, so they want the pressure at the second point, which is P2. So I'm just going to move this around. They want P2. I just need to multiply this over. P1 on N1 T1 times N2 T2. Okay? So that's what I'm solving for. Yeah? Now, let's go grab our numbers. Okay? You guys can help me out actually. This is the question. What is P1? Grab the numbers for me. What is P1? There's only one pressure in the question. You just have to pick that one. 338 is K. K is Kelvin. Kelvin is temperature. So for pressure, I'm looking like pascals, kilopascals, ATM. Yep. So this is P1. What is T1? What is the first temperature? Okay, cool. So that's T1. And what's T2? Yes, 338 kelvins. Okay, this is T2. All right, good. The only thing I have left is moles. I don't get given any actual number for moles, which would be an issue if I wanted to sub in n at a single point in. But luckily here, I'm not just dealing with n, I'm dealing with n1 combined with n2 and how they relate with each other. Yeah? Guys, at the start, you have PCO5. There has to be ways of getting around the question. They don't always have to give you moles. If they did, it would be easy. And then at the start, you have PCO5. The question tells you it completely dissociates into PCO3 and CO2. PCO3 plus CO2. Okay? Tell me, how many moles is there at the start in the equation? You started off with 1, so that's N1. Yeah? How many moles do you have at the end of your equation? 2. All right? Okay. How did you get from N1 to N2? N1 is 1, N2 is 2. How do you get from 1 to 2? Times 2. Good. N2 is twice N1. Yeah? N2 is twice N1. Each gas you break at the start turns into 2 gases at the end. Each gas you break at the start turns into 2 gases at the end. I don't actually need to know what the actual number is. I always know it's a 1 to 2 ratio in total. For anyone that doesn't know where I got the 2 from, guys, there's one PCl3 and there's one CO2. There's 2 gases total. One is PCl3, one is CO2, yes, but there's 2 gases in total, right? So N2, the second amount of gas, is twice the first amount. I'm gonna sub that straight in, okay? Guys, can you just imagine this in your head? When I sub this straight in, do you even need to know N1? Imagine yourself subbing N2 is 2 times N1. Do you even need to know N1? What the number for N1 actually is? Let me put this in for you. Good. No, I don't. Why not, guys? Because what happens to N1? Mathematically, it just gets cancelled out. You don't actually need to know what it is. Yeah, it just gets cancelled out. You do not need to know what it is. Okay, so then I'm gonna pop in my numbers. P1, you guys said was 25.5 kilopascals multiplied by 2 multiplied by N1 multiplied by, oh, my N's will cancel. So let me just get rid of that now. Multiplied by 2. And then T2, you guys said was 480. That's the final temperature. And then remember, my N1's canceled out. I don't have N1 down the bottom anymore. And then my T1 was 338 kelvins. What is your second pressure? Is T1 not just under P1? Oh yeah, it is, but then you know when you're multiplying, you kind of just combine the whole thing. Like this isn't like you're adding where it has to be separate, right? If you're multiplying, it'll just go together, yeah. 72.426 dot dot dot. And then keep the same units. Your kelvins cancelled out. The only unit left is kPa. Okay. And then round off as usual for your calculation questions. Yeah. Guys, you prepare a lot for your yearly exams. The chances that you read a question and you're like, I actually don't know where the number is very slim. Okay. If you look for like 5 minutes in your exam and you can't find the number, chances are it just cancels out and you don't actually need to know the number. Okay. So be wary of questions that you feel like you don't have enough information for. It probably cancels out, so you don't actually need to sub something in. Yeah. Okay. Good. Similar next question, but taking it slightly a step further. Gonna move this one out. All right. I need you to keep in mind what, before we go on to the next question, keep in mind what the question that we just did said. Yeah. The PCl5 completely, which means there's none of it left, it fully turned into PCl3 and CO2. Okay. That's why we were able to say that whatever one of the gases turns into two of something else. There's none of it left. It completely dissociated. I don't have to worry about any PCl5 left. That's why I could read the ratio 1 to 2. Okay? Be very careful with this next one. Ammonia is created according to the balanced equation below. 3H2 plus N2 turns into 2NH3. The reaction is allowed to take place in a rigid container. 8 moles of hydrogen gas are mixed with 2 moles of nitrogen gas. The initial pressure exerted on the container is 5 atm. Assuming the reaction runs to completion, what will the pressure exerted on the vessel be after the reaction takes place? Okay, I've got some moles, I've got some pressure, temperature, volume are not mentioned. I can't use the ideal gas equation, but I'm going to use a version of it. PV is nRT. Apply what you learned from the previous question, the notes that you took down. What's question number one? What's changing here? What variables do you want to move to one side together? What's changing? Pressure is one, good. And what's the other one? The reaction occurs, which means the moles you have at the start won't be the same as the moles at the end. So number one is pressure. What's the second thing that's changing? The moles. Good. So pressure and moles, I'm going to move to one side. Now let me move my N over to the left. And then guys, just for the sake of making sure you get it, what do you want on the other side? What's staying the same? What hasn't been mentioned in this question? Just list it out for me. You can just give me the letters. V hasn't been mentioned. R is your ideal gas constant. Temperature hasn't been mentioned. Exactly, good. So I'm going to move because I kept P on the left, I'm going to move V over to the right, RT on V. Good. Okay, so then again, the pressure on moles at any one point is equal to the pressure on moles at any other point. P1 on N1 is equal to P2 on N2. Okay? Read the question again for me. What do they want? Do they want P1? Do they want N1? Do they want P2? Do they want N2? Because I'll rearrange the equation in the format that they want it in. All right, cool. They want the pressure after, which is P2. So I'm just going to rearrange this now. P2, oh, P2 is P1 on N1 multiplied by N2. Okay, now pressure is going to be the easiest one to figure out. What is P1? 5 atm. Okay, now N1 is also going to be easy to figure out because N1 is what you start off with, yeah? How many gases in total? What did they put into the container? There's eight hydrogen, yes, but that's not the only gas in the container. There's eight and there's two. Good. What's the total then? The total is 10, yeah? So 8 plus 2 is equal to 10 mole initially. All right, now this is where it deviates from the question that we just did, yeah? Does this question tell you that all 10 turned into the stuff on the right? Does it say like, oh, completely dissociated? Does it say that? Does it say that? It says they mixed. Does it say, mm-mm. Oh, assuming the reaction, oh, sorry, you're right, yes. Assuming the reaction runs to complete. All right, now here's the thing though. I have to change my phrase. I didn't see that part. Assuming the reaction runs to completion, okay? With the previous question, how many reagents did you have? How many formulas had to convert? What's on the left-hand side? One formula or two formulas or three or four? In the question that we just did, one. Yeah, on the left-hand side, you only had one reagent. So you were only concerned with breaking that thing down into the right. Okay. However, in 32, how many reagents do you have? Is it only one as well? They're interacting. There's two things on the left. Okay. There's two things on the left, which could mean it's possible that they get added in ratio and they both fully turn into the right. But what's the other possibility? They might not be added according to ratio, and there might be one that's what? What kind of reagent? There might be one that's in excess, which means the other one is limiting. Good. Okay, when you're dealing with one reagent, like in the previous way, it just breaks up. You just break up however much of it you want. Here, it depends on the interaction between your two reagents. If they're not added in ratio, if one is added less than the other, one's limiting, the other one's excess. Now, guys, if it's limiting and excess, it's not according to ratio. If it's not according to ratio, you cannot read it the way we did the previous question. Okay, if it's not according to ratio, you cannot read it the way we did the previous question. Now let's check though. Let's check. Maybe it is in ratio. Okay. The hydrogen is 8. So that's the 8. And then the nitrogen is 2. Okay, that's the actual amount that we added. What's the ratio in the equation? What's the correct ratio? 3 to 1. Okay, that's the correct ratio. If we want to make sure it's in ratio, you do 3 to 1, you do 6 to 2, you do 9 to 3. Is the amount they added in ratio? Mm-mm. Okay, it's not, which means, unfortunately, we can't get around it. You have to check for the limiting reagent and figure out what's left over. Yeah, so this is how much they added at the start. Let's make a note of that carefully. This is N1. And then N2, we have to figure out what's left over. So now I don't have enough information to fill this out. I've got P1, I've got N1, I need to look for N2. So here we have to do your stoichiometric ratio work. So 3H2 plus N2 turns into 2NH3. So it was 8 moles hydrogen, and they said 2 moles nitrogen. So you guys figured out that it's not in ratio. We have to check for the limiting reagent. How do you check for the limiting reagent? Take the moles, divide it by what? Take the mole, divided by the coefficient. Good. If they haven't given you moles, yes, you go look for it. Luckily here they didn't, they were, they felt like you had enough going on already, so they gave you moles. For hydrogen, it's 3. Tell me what number you get for that. And then for nitrogen, oh yeah, it's 2 divided by 1, which is just 2. 2.67, cool. And then your limiting reagent is smaller number or bigger number? Smaller number. Okay, which is the N2. So this is smaller than 2.67. So therefore, N2 is your limiting reagent. Okay, cool. Guys, Moles at second point, this N2 here, is all of the gas that's left over once the reaction's done. You remember point one is at the start, point two is at the end. It's at the end of the reaction. Okay? So guys, N2 is the limiting reagent. When the reaction is done, does N2 exist? It's the limiting reagent, it's been fully converted. No, N2 doesn't exist. Good, so there's none of this, okay? Because it's been fully reacted. Tell me what does exist then? What gets made during the reaction? What's on the right-hand side of your arrow? What gets made during the reaction? The ammonia, good. And then because H2 was in excess, it's left over. So by the time the reaction's done, will I still have some H2 left? Yes, good. Okay, you are used to doing questions that ask you how much product gets made. Be very wary of questions that ask you what's the content of the beaker, because that's not just what gets made. That's also what didn't get fully converted. H2 is still left over. So you don't have any more of this. The NH3 is easier to figure out first. Yeah, so let's do that first. It'll be easier. Moles of NH3 produced. What's the ratio of NH3 to N2, your limiting reagent? I'm trying to figure out NH3, and then N2 is the one that's the limiting reagent. Yeah, 1 to 2 or 2 to 1, depending on how you read it. But I'm going to the NH3, so I'm timesing by 2. So then, guys, if your limiting reagent is 2 moles of N2, how many moles of NH3 are there? It's a 1 to 2 ratio. Times by where you're going. 2 moles, 2 moles. Where did 20 come from? Oh, you're doing the 10 at the start. Okay, 10 was the total, yeah? Here I'm only relating it to the N2. Okay, N2 is your limiting reagent. 2 moles of N2 fully converted into NH3. You're only using the 2, 4. Good. So NH3 produced is 2 times moles of N2 is 2 times 2 is equal to 4 moles. Good. All right, that's not the only thing in your beaker because you guys said H2 is left over. Okay? The amount of H2 left over depends on how much you put in and how much gets reacted. So for H2, the amount added was the 8 mole at the start. Okay? Because that just came from the question. Yeah? The amount reacted, because remember, how much is left over depends on how much you put in and how much got reacted and taken out. Yeah? So I need to know both. Added is 8. What's the ratio of N2 to H2? 1 to 3. So then you times by 3. So then if there's 2 moles of N2, I don't care about the 8. I'm figuring out how much reacted. Leave this for now. If there's 2 moles of N2 reacted, and it's a 1 to 3 ratio, how much H2 reacted? You reacted 2 moles of N2, it's a 1 to 3 ratio. How many moles of H2 reacted? I don't care about the 8, that's how much I added. You guys said it wasn't in ratio. I just care about the 2. 2 times 3. You're going to the 3, guys. You're going this way, yeah? Be careful. Don't lose your basics as we do the harder questions. 6, good, you're timesing by 3. Okay, so reacted is 2 times the moles of N2 is 2 times 3 is equal to 6 mole. All right, guys, you added 8 moles of H2, 6 of that got reacted. How much H2 remaining? 8 minus 6 gives you 2 moles remaining. All right, cool. Guys, 4 moles of NH3 got produced. There's 2 moles of H2 still left over. Moles of gas remaining. Oh, so moles of gas when the reaction is. So when the reaction's done, there's NH3 left and there's H2 left. There's 4 NH3, there's 2 H2. How many moles of gas in total by the time the reaction's done? 4 NH3 got made. 2 H2 is still left over. It didn't go anywhere. So at the end, you have 4 moles of NH3, you have 2 moles of H2. How many moles of gas in total? 4 plus 2 gives you 6 moles left over. This is N2, moles at point 2. Yeah, this is moles at point 2. You now have every single number to pop into that equation that we figured out earlier. Okay, you now have every single number to pop into that equation earlier. All right. Okay. So let's bring it down. So it's all in order. The equation you guys got, P2 is P1 on N1 times N2. P1 you guys found in the question before. You guys said that was 5 atm. And then mole 1 was just the total that they put in. You guys said there was 8 from hydrogen, 2 from nitrogen. So in total at the start, there was 10. And then N2 we figured out now. There's 6 moles in total left over times 6 moles. What is your final pressure? Or you could do this in your head. Okay, good. All right. 318. Yeah. Yes, yes, the moles cancels out. So mole cancels out with mole, and then the only thing you have left is 18. Okay, very good. All right. As always, you know any questions, just keep them coming. All right. Okay. 22. One method of synthesizing ethanoic acid involves the oxidative fermentation of ethanol in the presence of bacteria. The equation, does this sound familiar to anyone? Biology? The equation representing this reaction is given below. As given, in a small scale experiment using this method, it was found that 23 grams of ethanol produced only 4.54 grams of ethanoic acid. Calculate the percentage yield from this experiment. Percentage yield is this. Percentage yield, I'm going to give you the proper equation first. Percentage yield is experimental yield over theoretical yield. And then guys, how do I turn things into a percentage? Times by? Times by 100. All right, that's your proper equation, yeah? In colloquial terms, it's this. In a way that makes more sense, it's how much you actually made during the experiment over how much your calculations say you're supposed to make. Because the calculations is the theoretical part. Experiment is what you did in the lab. How much your calculations say you're supposed to make. Times 100. Okay, because things don't go exactly as planned. Conversion is never really 100%. Okay. So they've told you in here that they reacted 23 grams, they reacted 23 grams of ethanol. And you're supposed, oh, sorry, they only produce 4.54 grams of ethanoic acid. Yeah. This is how much they reacted. And the experiment, only EXP, I'm just shortcutting for experiment. Yeah. 4.54 grams. I bet you when we do the stoichiometric calculation ourselves, you're going to get a bigger number than that. Yeah. Let's check if that's true. Okay, so they've given you the experimental amount. In the question, that's the 4.54 grams. We're going to do our own stoichiometric calculation to figure out how much they were supposed to make. Yeah. when we do harder questions, the basics kind of go back out the back just because you haven't done it in a while. Yeah. So back to your basics a little bit. Ratios in a balanced chemical equation gets read in terms of, if you're going to use an equation, we don't use 23 grams, we use moles. So step number one is going to be converting whatever they've given you into moles. Here they've given you 23 grams. It's a mass. What equation are you going to use to get to moles if they've given you mass? Mass on mole mass. Moles of C2H5OH. Mass on molar mass. They've given you 23 grams. Guys, C2H5OH is ethanol. It's in your alcohol drinks. Alcohols are actually a bunch of different things, but when people say alcohol in like real life, like drinking alcohol, that's ethanol. It's 46.068 grams per mole. What is the moles of ethanol, please? 0.4992. And then we said if you're going to read the ratio, you're going to need to do it in terms of moles. They want me to get to the acid. Yeah, so you're looking at this guy. What's the ratio? 1 to 1. So the moles of the acid should be the same. So moles of CH3COOH is moles of ethanol. It's a 1 to 1 ratio. So 0.4992. And then guys, I need to get back to mass because if I'm going to do percentage yield, they need to be the same mass so they can cancel out. They've given me experimental yield is 4.54 grams. I want my theoretical yield to also be in grams. How do I get mass from moles? It's not mass on molar mass because I'm not dividing by molar mass. What am I doing instead? I'm timesing by molar mass. 0.4992. This one is 60.05 grams per mole. And what's the theoretical mass of the acid? 29.98. Thank you. I've got my theoretical mass now. I'll just pop it back into my equation. So percentage yield is experimental yield over theoretical yield. The experimental yield, they told you they made 4.54 grams of said acid. And then your calculations tell you were supposed to make 29.98. What's the percentage that they actually made? Oh, I'm expecting 15.1% to 3 seconds. Round it off. Okay. And then there's like a part B that's like, judge how well the experiment went. Did this experiment go any good? No. Okay. Because you should ideally be getting, you don't normally get 100% conversion, but it should be a lot better than just 15%. Yeah. All right. Very good. How are we? Are we alive?